Okay, let's begin lecture. We have just finished handing back homework 2 from Daniel's pile. And tomorrow we'll do it again, homework 3. And we just were talking about homework 3 in office hours, and we had a good, I don't know, I thought it was a pretty good session. So about homework 3, a few things to review. I uploaded the regular PDF of yesterday's DocCam session. I did that this morning. And so if you need to double check the diagram of the Calutron example, yeah, I mean, it's right there on the screen, and you get the big version of it in the PDF. You can sure do that. Figure 21.12 is also nice, but it's just kind of small is all. But it's nicely done. It's in the margin of the textbook. And Daniel's graded all you guys. I already have my pile in a spreadsheet ready to upload, and I'll get Daniel's grades a little bit later tonight. All right, so the other thing I want to, as far as the homework, a couple things. I want you to work really neatly. There's a lot of calculation in it. There's nothing too grievous. I mean, we've done it in lecture. So but you still have to put a lot of things together, and you have to do a little bit of thinking, but it's going to require a little bit of real estate. Now, if you have messy handwriting, I didn't take anybody's points off, but I did notice that some of the people I graded were pretty messy handwriting. But try to be as neat. You know who you are. If that's you, just try to be as neat and compact as you can be. All right, now a diagram something like the upper half of this one, might be nice, or would be nice, because I'm going to be grading your diagram as always. Pay attention to where I specify in the handout where your round off is. So for the speeds that you have to calculate, it's to the nearest meter per second, and that's going to be 5 significant figures. Now you can do everything at 5 significant figures in the speed calculation. All right. The radius calculation, you know what the 2 significant figures is on the radius calculation? We were just talking about it in office hours. It's the size of the magnetic field. I specified that as 0.10. But anyways, I want you to go 3 significant figures. So we'll just assume the magnetic field is 0.100 Tesla. And then you could do 3 significant figures for the radius of curvature of the track for each of the 2 isotopes. Okay, so there's even a little section on it in the textbook on the mass spectrometer is basically what we're doing. And for those of you that are heading for some kind of a medical or scientific or biological career, mass spectrometer is in your future if you're going to do any kind of investigative work especially. Now here's another diagram, 21.14. This is similar, but it's a different geometry. The geometry that I want you to use is this one back here. In other words, a 90-degree turn from 9 o'clock to 12 o'clock. That's the one that we used in class. That's the one I want you to use for judging the separation of the 2 beams of isotopes. But you can still look at this. I mean, it's got a bunch of good equations and whatnot. But this diagram down here, this is basically another collector. And this one's a full 180-degree turns. So our device is 90-degree turn.
But when you say that, basically, like our diagram should show like how the two different particles veer off.
I want you to show me a diagram with the track of each isotope, an example track for each isotope. All right, so yeah, this one has two different isotopes, or two different particles anyways, two different ions. All right, I want to add a comment. Last time, you can still see my diagram that I chalked in on the chalkboard about the uniform magnetic field. 21.3 is a nice diagram, and I'll draw your attention to the first two. This one, bar magnet field. It's a dipole field. This is a bar magnet with iron filings. You know, you do it when you're a little kid in 6th grade and whatnot. I still like to do it. You know, experiment with the iron filings and bar magnets and stuff. But now this one over here, that's the horseshoe magnet. This is figure 21.3. And I want to talk about it a little bit. Here's a close-up of it. The horseshoe magnet. Right in here is the sweet spot. And I mentioned that a lab might not use a bar magnet per se, but it might use a horseshoe magnet, because right in here, if those two metal faces are fairly close together, the magnetic field is going to be very uniform and very intense. It's both things that you want. If you're trying out some magnetic effect, you want the magnetic field to be as big as you can. You don't want it to be a little teeny magnetic field. You want a good sized one. And it helps if it's uniform. So let me move this out here. Yeah, see, so this is the sweet spot in here. And this is where you would, want to put your sample carrier, and, any other devices that you want to put in there to study some kind of a magnetic effect. So that's in the lab. Now we're going to talk about solenoids here this morning, and loops of wire. And solenoids also form a fairly nice uniform field, but different geometry. All right, so here's our main topic for this afternoon. We're going to calculate, and we're just going to do a couple examples here. I'm going to give you the basics, then we're going to go to the document cam and calculate a couple Cinci magnetic field strengths for a set of loops, and then something called a solenoid, which is a little bit different. So the first thing that we'll do is we'll do loops of current. It's page 597. Here's a nice diagram, figure 2130. And what I want to draw to your attention is that the right-hand rule that they use, let me get my cursor over here. All right, here's the right-hand rule, 2130. And what they say is that the direction of the magnetic field in the center of the hoop, so the central field, not the external field outside the hoop, but, and there's other right-hand rules out there, but, and a bunch of calculus, cross products and all that stuff. But at the center, your right hand will do the job, and that's significant. And what they do is they put the thumb in the direction that the current is going, and then they curl the fingers around and say that the direction, like your index finger here is pointing, is the direction that in the center of the wire loop, that's the direction that the magnetic field is pointing. So, and I'm going to give you some clicker questions, see if you can get this one. All right, so make a note of this, make a diagram of it. Yeah, thumb in the direction, so if you're in the front of the wire and the wire is going this way, your thumb is up. Now, if you want to think about the other end of the wire, the other side, the far side of the wire, okay, the current's going to be going down over there. So you got to bring your thumb downward, and then your fingers are still going to be pointing this way. So the magnetic field is still pointing this way. And they compare it to a bar magnet and a dipole field. So it's like having the N side of a bar magnet in that orientation. And that's and look very carefully at the way that the current curves around there. Now, I'm going to give you a diagram here in a second for a clicker question, but before we do, let's do the intensity. For a single circular loop, the central field is mu naught, the magnetic constant mu naught, which is 4 pi times 10 to the minus 7 in our metric system, divided by 2r. And r here is not the resistance of the wire, but the radius of the loop. All right? And this is idealized. If you're down here close to where the loop breaks and you go back down to the battery, you know, down here it might not be exactly that. But towards the center, yeah, it's pretty good. All right, now if you have a bunch of circular loops, capital N, the number of circular loops, you just multiply that result by N. All right? All right, so if you have a bundle of loops, you know, taped together, and they form a really nice electromagnet, you know, and stuff will get sucked into it, you know, a little, you know, tiny piece of steel, you know, like a screw or something like that. If it's strong enough, it'll get sucked right into the center of it from either side. So, and so this is the intensity. Now, what we're going to do is we're going to calculate how many loops, N, how many capital N loops are needed for a 0.100 Tesla magnet. You know, and that's the one that we've been using in our device and stuff. So we're just going to do, you know, 0.1 Tesla is a easily achievable magnet. And what they do is, you know, in first grade or in sixth grade science fair, you take some wire and you wrap it around a nail and connect to a battery. Usually, you do that with some pretty thick wire, you know, a big diameter wire. But in a real application, they take really fine gauge wire and do a zillion loops, you know, or a zillion loops per centimeter, you know. With really fine wire, and that's because it's a little more efficient. But anyways, we're going to do an example of that here in a few minutes. The other thing that we're going to do is a long solenoid. This is from page 598. And they even define the word long in terms of the radius and so forth. Here's a picture of it. This one also has a right-hand rule. It's a little similar. But now a solenoid is basically a bunch of loops kind of stacked, right? So that the array has a length factor. All right? And the thing about this, in a, you know, you got a loop up on the top there, and so there's your right-hand rule for a loop. And it's basically the same thing for a solenoid. So the north or the magnetic field lines are going right through the middle. I like this picture down here, by the way. That's a dipole field. You know, so a loop in itself, one loop will form a dipole field, and the stack of loops will form a dipole field. All right, and so you put your thumb in the direction of the current in any of the loops that form the solenoid. Any loop in the stack. And look at this down here. This row of circles signify current that's coming out of the paper. So sometimes you can figure out between this perspective view up here and this cutaway view, this cross-sectional view, you know exactly how to handle the current. But as I've mentioned last time, it's tricky trying to work in perspective, especially if you don't have your contact lenses. But trying to work in perspective with these three-dimensional forces and fields and stuff can be tricky. Anyway, so the current comes out of the page down here, and it goes into the page over here. So that means it's kind of going around like this. all right? And notice that my thumb of my right hand points in the direction of the magnetic field lines. And that's the right-hand rule that I use. But the textbook uses thumb in the direction. So here's the thumb of the right hand, coming like this, okay, the direction. So if I go to, this side of it, the current's going up, and I curl my hands around to the inside of the wire, and it's still going leftward, and all the way through. And it has a dipole shape. And the intensity is pretty simple. The field strength goes by the number of coils per unit length. That's lowercase n. So that would be a number per meter or a number per millimeter or something like that. Question?
Could you repeat your hand again? The one that you use?
Yeah, the one that I use is curl your fingers in the direction of the current like this, and then your right thumb of your number one right hand points in the direction of the field lines in the center. Now, both of these right-hand rules are for the central field. Now, why is the central field important? Well, this is a sweet spot down here. Go ahead and, if you've drawn a picture, see if you could draw a picture of this lower one here. Take a few minutes, draw a dipole field. That's a good sweet spot down there. It's not perfectly uniform because it's a dipole, but depending on how big your sample carrier is and whatnot, here's the sweet spot, Let me get it back in there. Okay, there it is. Okay, so that sweet spot, yeah, you want to put your sample and your devices down there. Or, ... possibly, you want to put a patient in there if your patient is getting an MRI. Yeah, when you put a patient into an MRI machine, you're putting him into a ginormous solenoid with a lot of juice going through it. And I've never had an MRI. I've seen the machines and stuff, but I've never had one. I imagine you get kind of claustrophobic. And how long do you stay inside the actual solenoid? Like for just 30 seconds? 20 minutes? Get out of town. Are you kidding me? Oh my goodness. Do they have movies in there or something? No? They don't give you virtual reality glasses, Do they have music? They better. Boy, I hope I never have to take an MRI. That would be, whew, I would not like that. Anyway, so this is figure 21-32. Now, what we're going to do is we're going to do another example of this. Another 0.100 Tesla solenoid. Now, the magnetic field strength inside of, I'm going to have to look that up, inside of an MRI machine. I am not up on my MRI machines, but you should be able to look it up. It's got to be one of the specs for the MRI machine because of what they do, the central field, the sweet spot. Anyways, so that's where the doctor puts you. Now, I want to give you a little blurb about these constants, these dipsy mu naught and epsilon naught and stuff. Mu naught is called the permeability of free space. And it dates back to the times when they thought that magnetic field lines of force were actually permeating a medium. Excuse me. Free space. And we still use the term, and we still use the constant, because it's kind of, and here's the value of it, 4 pi in our version of the metric system. So with Teslas and amperes and stuff, mu naught is 4 pi times 10 to the minus 7 Tesla meters per amp. Excuse me. And the related constant, which we've seen last week, epsilon naught, is called permittivity of free space, and it has this weird value, 8.854 times 10 to the minus 12 coulombs squared per Newton meter squared. So it's a weird, I don't know what that is. But the interesting thing, the reason that they use them is that even though they're kind of yucky looking, they actually encode the speed of light. So it's worth just simply knowing this as a footnote to history. So on exam 2, you know, true, false, or matching. You know, think of it. And for those of you that have been thinking about, you know, altering your study methods and stuff, here's something that you can think about. Every topic that we talk about in a given lecture, you can ask yourself, how would Dr. Brickner make a true-false question for exam 2 out of that concept? Or how would Dr. Brickner use this formula in matching? Or how would he use this calculation and modify it? You know, because the homework that we had, in case you guys didn't figure it out, the homework was meant to prepare you for the calculation, the electric field and electric potential calculations on the test. Because secretly I knew it was going to be on the test, and I didn't tell you, but those homeworks were meant to help you with that. And I had a student, well, I'm not going to share what the student told me, but I think it was meant to be helpful for you for producing that on the exam. So every time you see a homework problem that I write, ask yourself, how can Dr. B modify this maybe and put it on an exam in a tougher form or maybe an easier form? Now, the form that you had on the exam was a little bit easier than the homework, I think. Yeah, because that one in web courses is really, it wasn't fancy, but there's a lot of places to make a blooper. But anyways, to use that as a study technique, you know, what would Dr. B how would he take this concept or calculation and put it on exams similar to what I did on exam 1? By the way, a student asked me this morning in discussions about what are the sections in the chapters that are going to be on exam 2. And definitely chapter 21, 22 that will start today, 23 that will start on Monday, and finish on Tuesday morning, or Tuesday first half of the lecture before the test. We're about half a lecture behind where I want to be. But anyways, he's got a thread there. I can't remember who it was that started it, but it's in discussions, and I think I'll probably modify it tomorrow when we've done a little bit more chapter 22 and maybe a little bit of chapter 23 planning over the weekend. So I know a lot of you guys want to try to get reading it done ahead of time, and I've got all of chapter 21 mapped out in that discussion thread, so that's a good start. Anyway, so it's worth knowing epsilon naught and mu naught, even if it's only for true false or something like that. And the reason is that they encode the speed of light. Here's how it works. Here's our Coulomb constant over here, K. And that's 1 over 4 pi times epsilon naught. Now the square of the speed of light, c squared, as in E equals mc squared, that's actually just the reciprocal of the product of mu naught and epsilon naught. Now, I am not an expert at the metric system of electrodynamics has several different units, regimes that are designed for particle physics or atmospheric physics, similar to how in weather forecasting, you'll sometimes see people dealing with pressures in atmospheres, sometimes in millibars or bars, sometimes in millimeters of mercury or inches of mercury. You know, like inches of mercury, 30 point something is fair weather at sea level. And 1013.25 millibars is fair weather at sea level. So the fact is that because, you know, and that's like what people that work in weather and meteorology and stuff, they have different ways of using pressure because they're trying to bring out different, or they're trying to study different effects, bring different numbers out of the equations. You know, like some of them are trying to figure out the density of raindrops. I mean, believe it or not, they like to know that. But some people are trying to figure out the temperature of cloud tops, you know, from satellites. You know, and some people are trying to figure out, well, what's the wind going to be like on Tuesday next week? You know, and they'll be doing something different with pressure. And all those different pressure systems, PSI, that's another one. They're all different. They're useful for different kind of applications. In electromagnetism, some people use mu naught and epsilon naught explicitly. Other people use K, Coulomb's constant, and the speed of light. And that's what, you know, in theory of relativity, that's what we normally do. We use Coulomb's constant and the speed of light. All right? But it's kind of mysterious, you know, why this is the case, but it does seem to be true. 1 over mu naught times epsilon naught is the square of the speed of light. Now, I'm going to give you a clicker question here. Let's see if you guys can. Let's see if you can use the right-hand rule. So get your hands warmed up. That's right. And we're going to do right-hand rule. All right. And, you know, here's a preliminary question. Now, this one's not right-hand rule, but let's do it. Let me start multiple choice. So you should be getting your Go Nitro message. And here's your question. So just the conventional current direction. I see somebody. Now, you don't need to use a right-hand rule for this. You just got to look at the battery. You know, because this is a battery symbol down here. Some unspecified voltage V. What direction would the conventional current flow? Let me see what you guys are voting for. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 188 people just voted. That's great. And you guys are geniuses because, yeah, it's counterclockwise. What you get here is, you know, from the positive back around to the negative side. And 85% of you got that right. Yeah.
And so the magnetic field is what's coming after that, right?
Well, I didn't ask you anything about the magnet. This is just about, hush now. Just keep your lip. Because question number 2, I didn't animate it correctly. Anyways, okay, you should get question number 2. Perfect. Well, so I was, that was my next question, so that's. So anyway, so this thing's going around like this, and see how I do it? I use my fingers for the current, and then my thumb. But if you use your thumb, thumb going around this way, but then you got to curl your fingers around like this, and so it's coming out towards you. All right, so that's a circle with a dot. So make a note of it. Everybody gets a free question today, I guess. Who voted for B? Come on, they correct. Oh, I don't think I'm getting through to you guys. Anyway, I didn't animate that little red answer box correctly. But, so this gives you a good example anyways, even if it's not an effective question. It gives you a good example. Now, we're going to go to the document camera now. And we're going to do a couple calculations. All right? And I'm going to pause the YouTube for just a second. And we're going to go to the question. Yeah. Yeah, the current's going counterclockwise. All right, I'll face the screen. My whole arm is curving in the sense of the current. The right thumb is pointing in the direction. Now, this is the Dr. B right-hand rule for current loops, okay? Yeah, now I'll do it the way the textbook does it. Okay, they say take your right thumb and circulate it, but now you got to curve your fingers around so that they're, and see, I'm hurting my shoulder doing this. But here it is, all right? All right, so now my fingers curve around to the direction that the central field goes. So what you could do is go like this, and hey, you guys, if you don't want to dislocate your shoulder, what you could do is, like I was just, kind of, if it's a little awkward, just go like this and say to yourself, okay, here's my current, and my right finger's out now. Out here, this is outside. My fingertips are outside the wire. Okay, so if outside the wire goes in, then inside the wire, inside the loop goes the opposite. Because remember, it's a dipole field. All right. So so if you put your fingers out, here it is. Here's the counterclockwise flow. So if I keep my fingers up here, I'm outside the wire. But if outside the wire you're in, then back through the pipe, you're coming out. And that's using the textbook version. Yeah, and using your right hand. Yeah. All right. It's tricky, but Okay, let's question.
Just to clarify, so in your way, you curl your fingers in the direction of the current, and then the thumb will point in the direction of the magnetic field?
In the center of the loop, yes. So my fingers are the current. My thumb is the direction of the magnetic field at the center of the loop, and actually everywhere inside the loop, if you just care about the direction. And there's a formula for, we just did it. It's fairly simple. Okay. Now, what we're going to do is take a 5-minute break and come back at 4:05. And I'll set up for the document cam. Back to our YouTube. I want to talk about one more magnetic thing. And now we're going to be exactly one lecture behind the schedule, so I'm going to have to make it up. But I want to go from those 0.1 Tesla examples now, and I want to do parallel wires, and I want you to make a really, really careful sketch. So here are my two, hold on a second. Okay, so what I want you to do is to sketch in two parallel wires. They're going to be straight and as the textbook says, very long. And they give you a physical criterion for saying that they're very long. And we're going to separate them by distance r. Now I have a dotted line between the two wires. So in the two wires, they're parallel, so they form a plane. You could put a flat piece of plywood over the top of them. And this dotted line is in that same plane. All right, so they're separated by distance r. But what I want you to do is map in actually what all I've got is the currents. And I want them to be going in opposite directions. Now my current number 1 is going to the right. And my current to the right of this dotted line. Right? And my current number 2 is going to the left of the dotted line. So we're kind of above it and a little bit to the left of the dotted line. All right? And so these are anti-parallel currents. All right? And what we're going to do is, and I was talking to some students at the break, we're going to be doing right-hand rule out the wazoo here. All right? And hopefully this will give you another good workout. Because what I want to do is figure out the interaction. So draw in the current direction for both wires the way I have it. All right, so I1 and I2. And I don't have the wires drawn in, I just have the currents drawn in. And they don't have to be the same size current, but I've made mine basically the same size. I1 equals I2, but different direction, opposite direction. And it's two wires and they're separated by some distance r. All right, now here's the next step, and it's the tough one. We're going to draw in the field lines around one of the wires, number 1, so that one of the field lines is of radius r. So here's what it looks like. Now, and I did this really carefully. It took about 20 minutes to get this ellipse correct. There it is. All right, try to do. Now, that's the field line. It's blue, magnetic field line, from wire number 1. All right, so the center of that field line, long straight wire, circular field lines, the center of it is the wire itself, or the arrow that I have to represent the current. All right, so this is kind of, and what I did is to set it up so that field line goes directly through wire number 2, because it's the field line that you would map in if its distance from wire 1 was equal to capital R. All right, and you could draw a field line in there; it's perfectly fine. You know, then your next one might be a little bit further out, and even further out, and even further. And you know, because the magnetic field gets weaker as you get away from the wires. Now, this is not for any other wire; it's only for number 1. All right. And what this does is it allows us to figure out the direction of the magnetic field at wire number 2. All right? Now, the right-hand rule will then allow us to figure out the force on the charges that are moving along wire number 2. All right? So let's look at this. Let's use right-hand rule for the magnetic field lines. All right? And I want you to think. I hope everybody got some sleep last night, or at least a little bit before coming to lecture. All right? So you've got a field line. The current is going over there. Okay? So in the direction of my right arm. So there's your current. Current number 1. Okay, we got a circle around it. All right? So, and it's perpendicular. You know, the plane of the circle is perpendicular to the current. Okay? So we could kind of see it in perspective. But what direction are the field lines? I mean, would you, you know, is it like this, or are they, you know, how do they, what's the direction? What's the circulation of I see guys using their right hand. What is it going to be? It's going to be into the field, right? Into the paper? No, it's not. Okay. Here's the Dr. Brickner method. Thumb in the direction of the current. Okay. And then field lines, so they're going to go up over the top, down in the very front. So at wire 2, the field line is down. And then back around, here's me hurting my elbow. Back on the far side, the field is up. So this is what we got. All right, try to sketch that in. Now, if you feel like it, you could put, so you get your right hand in the direction of the current. So back on the back side, my fingertips are going up front. But around on the front side, my fingertips are going down. You know, my thumb is still in the direction of the current. And, brother. Now, I'm about to burn your brains into a crackly crunch because I am now going to give you a short answer question. So hit the refresh key on your calculator. Hit refresh. And because the next question has more than 5 options. Now, all you have to do is type in a letter and hit the send key. But here's your, and read carefully and, talk with your neighbor. You know what I just did? I just tangled up my cable here. Just wrapped myself up with this thing. Here we go. Work at 3 dimensions. Use pencils and pens if you want, and your right hand. In what direction is the magnetic force on a positive charge, conventional current, moving in the current I2 at point P? So right here's your point. Here's point P. In other words, the point closest to you on wire 2. All right, so think. And use your right hand and maybe your neighbor's pencil and pen, or if they have a meter stick in their knapsack or something. Hi. Oh, they were doing right-hand rule. Hi. V cross B, from V to B. Or use the textbook right-hand rule that's obnoxious. Only 22 people have answered. Very interesting. Oh, don't type in 2 letters. There's only 1 letter. 2 of you typed in. I want A or B or C or D or E or F, but I don't want more than 1 letter, so double check your answer. Okay, good. There we go. No, don't write in A, B, C, D, E, F. This is a serious question. What if I ask you this on the test for 5 points out of 50? You want to blow that? So the velocity of the current is also the velocity of the charges. So individual charges are going in the same direction as current too. Yeah. right hand, V, and wherever, find B. Okay? So if this is B, all right, so here's my B. I got to go like this, and I got to curl like that. Yeah, you curl them towards whatever B direction, wherever B is. Wait a minute. Wait a minute. So if this is my V, so I got to go like this and then up into this. Okay, so that would have to go like that, and so that the force would be that way. You just got to just keep working at it. And that's why I say use your pencils and pens and stuff. That might help out. Forget about wire 1. We already know all we need to know. The magnetic field there is downward at wire 2. We've analyzed. We're just trying to figure out what's happening to wire number 2 right now.
So like wire 2 is going like this, and that's the voltage must be going like that.
Just don't hurt your shoulder. No, not the left hand. Use the right hand. Okay. Yeah. What? V cross B. So wherever V is, curl it towards B, and then your thumb is the force. If you're using the Dr. B method. If you're using the textbook method, I don't know, it's something to do with the palm of your hand or something. I don't know. V cross to B. V curl to V is the velocity. No, it's the direction of the current. That's the direction of the moving charges. You think? Red shirt man? Yeah, but the current's coming this way. The current's coming across the room. Yeah, well, no. Fingers are, velocity is over here. Yeah, fingers curl around into the direction of the... Okay, 1 minute. I know you guys will feel good. By next Tuesday you'll have practice enough. Hopefully you'll answer simple questions. You can keep talking. I haven't called the question yet. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Come on, get your answer in. There's some of you that haven't answered. I mean, everything's voluntary, but... All right, now I want to show you what this distribution is. This is kind of interesting. I love asking these kind of questions. All right, now here's the breakdown. Okay, A, B, C, D, and E. So C and D are popular, but nobody's got S and E. Yeah, I don't know. Oh, F. Yeah, let's go down here and see what F is. Yeah, we got a bunch down here at F's. But you know, hardly anybody voted for A and B. All right, so A and B, and a lot of C and D, and a decent number of E and F. I hate this thing. It's just hard to... There it is. All right, let's go back to YouTube. All right. There's the stuff we got to think about. We don't even have to think about wire number 1. Current this way. So my fingers, magnetic field is down. Right thumb, right there. Away, and that was the biggest, that's the biggest vote, D. More people voted for this. Now, raise your hand if you voted for D. Yes. Raise your hands if you would like to get the answer correct next time. Yeah, okay, that's everybody. Okay, you don't have to raise your hand for that. But anyways, a good number of you got that right. It is not easy. All right? And I'll just be humble about it. I have made my share of mistakes, doing this. Right-hand rule, it can be tricky. Yep, here we go. Well, I did explain it. Here we go. Okay. The real explanation. All right, the real velocity in this perspective, let's say that current I2 is going across this way. Okay? So my right arm and my right hand and my right fingers are pointing in the direction of I2. Yeah, well, I'm just kind of rotating so that you can see it, so that now I2 is straight this way. Okay, so straight this way. And then the magnetic field is straight down. This is where I need a pencil or a meter stick. Okay, so I got to curl like this. And see where my right thumb is? See, you're not doing your right thumb the right way. You're holding your thumb like this. You got to hold it like this. That's what you got to do. Yeah, so do it. Oh my God, you're double jointed. I don't even want to look at that. Oh. Ooh. All right, without looking at you. So here we go. If you got to keep shh. Okay. You got to keep your thumb straight. Don't tuck your thumb in like this. Keep the straight like this. Like you're going to shake hands. Put her there in the old vice grip, like this. Okay? All right, so here you go. Thumb is out here. Right hand is in the direction of I2. That's where the velocity of the charges is. But my magnetic field is downward. I'm curling my fingers around to it. And so my thumb is now pointing out towards you guys. That's the red arrow. You're still doing it. Don't do that. You're All right. You know what I did? What I did when I was in grad school, I got a little piece of silly putty, or not, Play-Doh, And I took 3 pencils of different colors, and that's how I did it. And I just moved it around and, you know. All right. Shh. All right. Yeah, question. No, I don't know. There's the electric force, The student was asking about the electric force and the palm and stuff. The electric force, you don't need right-hand rule. It doesn't have that kind of configuration. It's not the result of a cross product. It's a scalar, it's a scalar charge times the field vector. So that's it. You don't have to do any velocity crossed with the field. Magnetic field you do. Now, you mentioned the palm. The palm is the way the textbook does it, and you do the one that makes sense to you, because if you can use the textbook palm method and get it right, more power to you. And I'll tell you what, I'll try over the weekend to work out this fancy palm method myself, see which one I like better. All right, now, let's keep going. I want to do another field point. Now this one, you can make notes. So add this to your diagram or make a new diagram. 2 wires symbolized by their current vectors. Distance r between them. The magnetic force on wire number 2 from number 1, F1 on 2. Magnetic force from 1 on 2 is in that direction, out towards you guys. Now, field point number 2, let's burn it in there. Field point J. Field point P we got squared away. Now, how about this field point? Now, what's going to happen here? Now we got current going this way, but what direction is the magnetic field from number 2? And I'll give you the answer. You can work it out yourself if you feel like it. The current's going this way in current number 2, and so the field over there, back over here, is downward as well. So go ahead and sketch in B2 at point J. It's also downward. And for that reason, I've got, all right, here we go. Ready? And using, now, no, you're not allowed to do it. Because I don't want your thumb to get paralyzed or anything. Okay. So V of I1, right? Curled to the downward B2. So, dun, 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 dun. Because current number 2 is going this way. And so, on the far side away from you, from number 2, the magnetic field's also down. Yeah, but that's right. The field from that was B1. B1 on this side was downward. B1 on the far side was downward, or was upward. Okay, that's not what we're doing now. We're doing B2 on the far side of. Okay, and current number 2 is going this way. So it's just like that. Bottom line, my wonderful students, is this: that anti-parallel currents repel each other magnetically. It's not an electrostatic force, although it's related to that. It is a magnetic interaction. And one more thing I'd like to bring to your attention. parallel currents attract magnetically. And that is what defines the ampere. And here's the definition of ampere. The ampere is that constant current which, if maintained in two straight parallel wires, now parallel, so currents go in the same direction. You're going to attract. Conductors of infinite length of negligible circular cross-section and placed 1 meter apart in a vacuum would produce between these conductors a force equal to 2 times 10 to the minus 7 newtons per meter of length. So every meter, you're going to get a certain number of newtons of force. And that's how we define the ampere. This and the coulomb is defined off this. So it's kind of a backdoor way to get to the coulomb. All right, it's 4:50. Let's dismiss. I'll see you tomorrow. Homework number 3 at 3 p.m. And those of you that want to get homework or anything like that, come on up to Naisha. Hey, homework? Yeah.